Eric, I'm going to hand the stage over to you.
All right. Thank you, Scott. Thank you, Scott. And happy to be here at the SAE International Software Defined Vehicle Summit. I'm Erick Richardson. I'm a systems modeling and collaboration consultant here at Dassault System. And today I'll be speaking with you all about systems engineering, empowering the development of software defined vehicles. So first off, a little bit about my background. I'm a systems engineer. My title is systems modeling and collaboration consultant, but at my core, I'm a systems engineer. I actually started with a degree in electrical engineering at Missouri S&T. And from there, I worked in different industries. I started off in aerospace and defense, working with Boeing and doing a role really where it could have been an electrical engineer, it could have been a mechanical engineer, really multidisciplinary from the start. But over time, I always wanted to understand kind of my part in the big picture. So I was introduced to systems engineering officially, even though I was already kind of doing systems engineering. I love doing it now because now we see, we're really trying to break down silos. And today we'll kind of get into what systems engineering is. But yeah, I've worked in material handling. I've worked in Internet of Things, different protocols, home security devices, things of that sort. But really excited to be here and talk about software-defined vehicles. If you click that QR code, that'll take you to my LinkedIn. So I love to connect with you on there. So let's talk about the agenda today. I'm going to hit on, first off, what's systems engineering, what's MBSE. I'm sure you all have heard that acronym somewhere. And a lot of times we use that acronym, but really don't explain it. So I want to do that today. Talk about systems architecture. Then we'll hit why we're managing this complexity for our software-defined vehicles development. We'll talk a little bit about the digital continuity of our workflow, going from the systems level to the EE level. Sam touched on EE architecture, so we'll hit it more on EE architecture, then going down to the domain of software. We'll talk about multidisciplinary collaboration, keeping openness throughout for our testing, also our verification validation activities. And we want to have traceability throughout for impact analysis and certification. Then I'll hit a couple of takeaways. So first, systems engineering. What is systems engineering? So we have a group called the International Council on Systems Engineering in COSI. It's our professional organization. And that's where we kind of get our definitions of what we mean when we say systems engineering. Different domains kind of have an idea of it, but we go by the INCOSI definition. And what is that INCOSI definition? So systems engineering is a transdisciplinary and integrative approach to enable the successful realization, use, and retirement of engineered systems using systems principles and concepts and scientific, technological, and management methods. So systems engineering or transdisciplinary. We're not just one domain. We're trying to understand all, the best parts of each of the domain, get them to work together, and then create an engineered system. So what's an engineered system? Well, engineered system is a system designed or adapted to interact with an anticipated operational environment to achieve one or more intended purposes while complying with applicable constraints. People say, what I say systems so much, what's a system? What's a system? The world is a system. So we break it down. The scope of the system we're talking about is an engineered system, and it's defined here. So when we talk MBSE, that's model-based systems engineering. And that's really the formalized application of modeling to support system requirements, design, analysis, VMV, verification and validation activities, beginning with the conceptual design phase and continuing throughout development and later life cycle phases, and on and on. It's a cycle. And we do model-based systems engineering. It's a way of doing systems engineering, but we're not doing it in a vacuum. We're just like mechanical engineering went to CAD, systems engineering is going to MBSE, model-based. So it's the application of these digital tool-based methods to accomplish the tasks and objectives and produce the outputs of the systems engineering process. So we have language, we have a methodology, different processes, best practices, and tools that we use to do this. So starting with systems engineering, that's at our core what we're looking to do. And a lot of times in model based, there's so many models. And now when we're talking AI, we're talking large language models, even small language models now. And so many people have an idea of what a model is. So when we're talking systems engineering or MBSE, we're really hitting on that systems architecture model. So we're at a level where we're trying to understand all of the things we need in our system before we go into implement it, and implementation and phases. So we're touching our requirements, we're understanding our user needs, our stakeholder concerns. We're doing some early V&V analysis, on the left side of the V, because we want to make sure that our architecture is right before we hand it down to the next level and thus forth. Because if we catch a lot of issues early on in the process, we'll save a lot of money in the end, save a lot of time in testing and rework later on. But with that systems architecture model, we then pass on that design intent down to lower level models. So there are specialized models for each of these domains, like mechanical models, CAD, electrical, fluidic, electronics, software models. All of these engineers or have specific tools that they may want to use to do their work, and models that are best for that low level intense work. So we want to feed up into the systems architecture model, but we don't want to confuse what we're talking about. So systems architecture models, and then all those lower level kind of design models that we're touching. So now that we started kind of base systems engineering MBSC, now let's talk about complexity for software defined vehicle development. So here I'm taking you to our 3D experience platform. At Dassault System, we have this 3D experience platform where you can do a variety, vast amount of different things with our different brands. But for software-defined vehicles, I mean, Sam touched on a lot of, how the market is going. But the market development, we're expecting these different things like the compute platform. So, enabling high-performance compute. These data centers everywhere. And there's so much growth that we expect to happen by 2030, going from 40 to 240 billion in that market. Things like the software platform. So creating these kind of containerized or modular software components that you can reuse and access from different ways. That's growing from 30 to 190 billion dollars. And then other data applications, all of these things are growing. So the market is here. We may have called it something before, software defined vehicle, and we'll continue to evolve the different names. But at its core, there's a lot of work being done and a lot of market that's growing that we want to be able to manage that complexity. So we're decoupling the hardware with the upgradable software. We're enabling over-the-air updates. We're also thinking about how we can modularize our hardware, so that when you have a vehicle that it's time to swap something out, it's easy to do. It's something that a customer might be able to do, or a shop may be able to do, and that customer can keep that car over the long term. Same way with software. There's a lot of things that we can just upgrade over the software instead of having to buy a whole new car. So what we're doing with that EE architecture, we're establishing that in the systems architecture phase, and then passing down that design intent to enable those vehicle experiences, both on board and off board, all kinds of experiences for your customers. Bringing in AI chatbots, bring it in, OnStar, all this kind of stuff. We want to be able to do at another level, and you have to understand that architecture before you go and implement it, right? So with that, let's talk a little bit about that digital continuity of our workflow. So we touched on the systems architecture level, going down to the design domains. So we start with systems, we go to EE, and then we go to software. So what is EE? EE architecture means electrical electronics architecture. So I'm a double E. My degree is in electrical engineering, but now this EE, what we're talking about is electrical electronics architecture. And managing the increasing complexity of products, we break it down in kind of three different pockets. We have, understanding what kind of equipment you need first. That's our hardware point of view. Then we'll understand which equipment does what. So now we're talking the software point of view. And then what information are we exchanging? So, what kind of communication protocols are we using? What buses are we moving information on? What's sent in a packet? All that kind of stuff we need to understand before we just say, okay, that's going to be somewhere down the line implementation, because we want that to hit our requirements of time, of speed that information needs to get from different parts of the vehicle to the customer. So we break that down, those three kind of pockets. And then, EE architecture really continues that digital thread for model-based systems engineering, from systems all the way down model-based design. We're connected to that upstream systems architecture model that I showed you. And here at Dassault System, we have the best-in-class tool we call CATIA Magic. It's also known in the field as Cameo, where that systems architecture is done. And I'll show you a little bit of some systems architecture from that. But it's a key foundation, came from automotive and rail, actually, and now it's relevant in all industries. So enables that digital continuity, and I'll show a little bit of that continuity. But we want to enable that because a lot of times that systems architecture was done in a vacuum, and then that implementation was done in a vacuum. So we're bringing that together so everything is connected and we have traceability throughout. So at systems level, we have that functional and logical architecture that we're done for our systems architecture. Then we're going that first step into the physical architecture, and we're splitting off these three design disciplines: electrical, electronics, and software. So then those designers can go on, and I'll show a little bit how the software continues to be developed. But the electrical, the electronics also continues to be developed, and systems engineers, we kind of bring it all together. So now going back to here, let me show you how with systems engineering, we're always thinking, okay, how are we hitting our requirements? We understand our stakeholder needs, but now here we're talking about an ADAS system. So we have under that ADAS system, we have things like an ALCA system, active lane change assist, lane keep assistant, the LKA, all these different requirements we want to hit. And this is from our systems architecture tool, CATIA Magic / Cameo. And this is a functional architecture in an activity diagram. So in our dashboard on the 3D Experience platform, we're able to see all of this work that's done by the systems engineers and all of the engineering teams. Here is a state machine diagram where we're understanding for the active lane change assist software controller, all of the different states that it can be in and how we want to design it for implementation. So we pass this design intent on down. Now at the next level, EE architecture level, we're talking the ALCA hardware. So we've abstracted down to the ALCA hardware that feeds up to the ADAS system. And here is when we talk EE architecture, we're able to map, if we understand our topology, our hardware architecture, understanding which ECUs, and Sam hit on, there could be hundreds of ECUs in these vehicles. Also in aerospace, we call these LRUs, line replaceable units, avionics units, things of that sort. Same concept, different fields call them different things, but same concept. Here's software compositions. We're breaking down atomic components, software to its smallest component, so then we can reuse that over time. So we're making software that's reusable, that we can manage, and always have access to. And we allocate that software to hardware, or we allocate functions to hardware. We can do that with our E plugin in our CATIA Magic system. So understanding which part of our vehicle, which ECUs, which sensors, which actuators, and even the communication matrices that we're going to use for that communication protocol. We can define that in the systems architecture. So now we're talking software. So we stepped into those three domains. We're in the software domain. So we want to hit those software requirements. As systems engineers, we're always thinking requirements. How do they fit our use cases? How do we have the traceability? Here, a lot of software is done in ALM tools like Jama, Jira, Tulip. We can also keep our code in a repository like GitLab. Software engineers want to use the tools they're familiar with. So they're going to see these different bugs, these different tasks, and they're going to keep those in those ALM tools. But here we have this source of truth at the 3D Experience platform where we can see into all that and keep everybody knowing what's going on in the grand scheme of things. So enabling multidisciplinary collaboration. Like I said, with those ALM tools, we have that openness. We, people can use the right tool for the job, and that's what we want to happen. So here, I'm going to show a little bit how we start that first step of coding from our state machine. Our systems engineer, we thought through, okay, how is this going to work in the real world? How are these states going to change? So we can start that first code generation, first level, and then it can continue to get developed in those specific tools. Here in the platform, we see our CAD, we see our BOM, we have access to understand all of these pieces of our vehicle as we're developing this software-defined vehicle. We understand our role in the grand scheme of things. So here, this BOM item of an ALCA active lane change assist, we have a software build associated with it. So that software, it's actually hosted in GitLab repository. So we can go in and see that C code. So going in and see this decision C code, right? That's hosted elsewhere in GitLab, but this is our source of truth where we can see, and when it's updated, we can understand which version is allocated to our ALCA system for whichever type of vehicle we're doing, for platform wise or vehicle wise. So then once we get that software, we want to validate it. We want to validate it in the real world, but we can also validate it in the virtual world. So we create these virtual experiences, these virtual environments where we can put the code that we are developing or we develop into different test cases in a virtual environment. So we've created these test cases. We want to understand, we're always thinking about requirements. So we want to understand how we're testing our requirements here. So with our validation plan, we're going in and we're seeing these ALCA test specs, and we're putting the requirements to the test cases. So we can have an allocation matrix here where we can then look at our traceability and say, okay, we tested this and these are the results. And now we've passed this test, so we've passed this requirement. And here we have a tool we call CATIA Scanner. So this is where we put that software into our virtual vehicle because we have all the CAD. And we're running these tests to understand how our software reacts. Does it match with our state machine? Does it match with our system requirements, our system design? So we can do all that virtual test and have that multidisciplinary collaboration. So now let's talk a little bit about traceability. Now, traceability, once we do those tests, a lot of times we use different frameworks. So depending on your customer, you may have to deliver in a certain framework. In automotive, ASPICE is one of the leading frameworks. So here we can we can match whichever framework you need, but here you put in your scope for traceability, and using this ASPICE framework, we can see how it's related to like the Jira data, the tasks, the software code, tracing all the way back to these stakeholder needs, because that's what we're looking to satisfy. So here we're going to an impact analysis, and we can see the entire digital thread. So all the way from the high level stakeholder needs that we've established to then system requirements that we've created, all the way to the tests that we are implementing to test these requirements, to our hardware topology, the sensors that we need, what is effects, some bugs that are out there. For instance, this target vehicle's tracking in the system requirements goes all the way to the tasks, SAN 2 and 6. So there's a traceability where we can understand if something changes, then we need to look into all of these things that are touching it. and then make sure that the impacts are not going to take us out of satisfying the requirements. So with looking at it from a systems engineering perspective, I talk a little bit about the takeaways. So, this systems engineering perspective allows us to have that single source of truth where we can see the work being done by all of the different engineers, the project managers, um, you know, everybody that's involved in the development process, making sure that we're hitting the customer needs. All stakeholders are represented. We have that single source of truth where we can establish a dashboard and see the information that you want to see. We have that end-to-end traceability where we can go with that ASPICE process or other frameworks that we use so that you can have that certification. Digital continuity throughout. And we do this for a bunch of customers. Renault in France is one of them, but there's a bunch of customers that are using these tools and these ideas. So that is my presentation. And if you hit that QR code, it'll take you. I'd love to connect with you on LinkedIn, and I will pass it back on over to Scott. Thank you all.
Thank you for that presentation. Thank you everybody for joining us. There's another presentation on stage one starting in a couple minutes, so be sure to hop over there. But thank you again, Eric. We will see you back here on stage two. Not you, Eric, but all the listeners.
Hey, you all enjoy.
Thank you.